Good afternoon, everyone. Communications and topology is one topic that PPL as a group has traditionally focused a lot on. And in the next 20 minutes or so, I'll try and spend some time just giving an overview of the. In the next 20 minutes or so, I'll try and give an overview of the work which we have done in last 1 year or so. And in the second part of the talk, I'll focus on one particular work which was published recently at supercomputing. First things first, communication in HPC is seen by a lot of people, rightly so, as a necessity but an overhead. So essentially, if you're given a choice that you have this 100,000 cores and you want to divide your work among those 100,000 cores and not spend any time on communication, you'll be happy and you just take it. Problem is, you can't do that. If you have those many cores and if your application is not delightfully parallel, they will talk. And if they need to talk, they need to spend time. And it's not much different from what we do in our day-to-day life. We're working in a group, we need to meet, we need to discuss. The trick is we should try and keep the communication time to minimal. However, I did some experiment. I ran a few applications that we regularly run on a few thousands of cores. And what I observed was, if things are not done correctly, you may be spending something between 25% to 50% time in performing communication. In essence, you can see this time as the time being wasted where the cores are not performing any actual computation. So our focus and of our work and in general is to make sure that we optimize it. However, communication is not that easy to optimize. There's a complex interplay of several components. The hardware, what kind of hardware you're running on, you don't choose that. What network properties are being provided to you, what interaction patterns your algorithm is following, and those kinds of things affect the behavior a lot. Also, as a user, your control over the communication resources is limited. When you're given 100,000 cores, you have total control over those 100,000 cores. But the network which connects them may be shared among users. So how much other users are using the network in comparison to how much you get, you don't control that much. And finally, as a system administrator, your goal is to make sure that all your users are happy, though your users may have contrasting demands. One may need more communication, while other may need less. So how do you make them happy? And then there's a diversity of application. Every application has its own communication pattern and may behave differently. Applications running on the system may have different patterns and they may behave differently. And finally, not all systems are created equal. Some follow a torus-based model, some have Dragonfly, some have fat trees. So optimizing things on this large set becomes a very difficult problem. And unfortunately, what we have found is you can't optimize, you can't do optimize once and run always. You have to look at system-specific optimizations. You have to look at application-specific optimizations and try and make sure that they are portable as much as possible, but that's how it goes. So the first set of optimizations that we have traditionally focused is on topology over mapping. So when you're running your application, you're aware of which cores talk to which cores. So when you place them onto the given set of cores given to you, make sure they are placed nicely. So if processor X is going to talk a lot to processor Y, let's try and put them on the same node. If not, let's try and put them on the nodes which are directly connected by a wire, not put them on the opposite ends of the network. For example, OpenAtom is one application which is heavily bound by communication. There are lots of FFTs which happen every iteration. What we did was we took OpenAtom. It also has a huge set of chars. Like there are around 13 sets of different chars which have different communication patterns. So we took those chars, we tried to analyze their placement or their communication pattern logically, and then try and place them. And this is what we see. For something running a large application on Vulkan, which is a Blue Gene queue system at Livermore, by use of topology over mapping, your timing can go down from something like 8 seconds per step to something like 5 seconds per step. And this scaling, these improvements can be seen across a range of nodes. Here, one may ask, why is that the scaling does not improve? This is one place which shows that no matter how smarter you get, your machine does impact what happens. So OpenAtom is bound by bisection bandwidth. And what we observed was when we were running on 1,000 nodes of Blue Gene queue versus when we were running on 2,000 nodes of Blue Gene queue, the bisection bandwidth did not increase. Hence, no matter how good an mapping we did, the timing did not improve. But at the same time, for a lot of other cases, the timing did improve. So it's always beneficial, but there are limits to it. Similar gains were seen for other applications or other use cases in OpenAtom. For more structured application, we have turned to a tool called Rubik. It's a Python-based scripting tool developed at Livermore. What Rubik allows you to do is to take your structured application or application whose domain can be defined by regular geometry, such as a 3D cube or something like that, and you divide those geometries both in application domain and in machine domain into different dimensions. For example, here is an application geometry. We know that most of the communication is within planes, so we divide them on plane basis. And then we take a torus geometry where we want the planes or the cores inside the application plane to be close by. So we want to put them into nice cuboids. So we divide the torus geometry into nice cuboids, and then we ask Rubik to map the planes to the cuboidals. This way, we tried these kinds of mapping in last year on two different production applications, Milk and PF3D, and what we observed was that depending on your mapping, your performance can change a lot and your performance can improve a lot. For example, for Milk, what we saw was while default mapping was doing very good and a lot of mappings did not improve performance, we still had one mapping which improved performance. Similarly, for PF3D, the default was really bad, but if you place them nicely, your performance can improve significantly. What we also observed was, I would like you to focus on something like a barrier. Traditionally, we think that barrier is a collective operator and its performance will not improve even though you do mapping. What happens sometimes is that the time spent is not in barrier, but the time spent is spent in communication imbalance that is across the system. So if you map them nicely, the communication imbalance reduces and your overall barrier time can go around. So far, this is like what we did with real applications. More recently, we have started asking more fundamental questions such as what determines the communication performance. We are trying to improve an entity which is getting us better performance, but why is it so that this kind of mapping is giving us better performance? How can we predict those kinds of metrics, and how can we quantify the effect of each of the metrics that we are seeing? We're also trying to explore the relation between the matrix which we have found or we have quantified and the actual performance. Is the relation linear, or is it higher polynomial, or something indeterminate? Or is there a statistical relation between this which can be exploited when we are performing such mappings? We have tried various methods. I'll cover one, but I'll talk about the other two. The first method we have worked on is supervised learning. Abhinav will talk more about this in a talk, I think the next talk. The second method is a packet level simulation in which you take your application, you generate traces, and you try and play them on really accurate packet level simulators. This allows you to do detailed study of what if scenarios. More importantly, it allows you to compare systems of similar sizes. A problem which we have seen often is if you are working on real systems and if you want to compare two different machines, let's say you want to compare Blue Waters with something like a Blue Gene Q, the two systems are so different in power and the capacity in this geometry, a fair comparison is difficult. But if you're if you are in a simulated environment, you can try and generate a topology which is similar. You can try and generate the capacities such that they match, and then you can actually compare if one kind of network architecture is better than the other. BigSim was among the earliest accurate network simulator. Recently, we have begun work on reviving the emulation and simulation capabilities of it. We have been using things like Codes, ROS, along with BigSim. Bilge will talk about this more sometime today. The third topic, or the third method which we have used, is modeling by Damselfly. What we found was, while the machine learning methods are very high level, statistical in nature, so they have aggregated the data in the end. So the prediction accuracy there may be low, or the use cases may be low. At the same time, the packet level simulation are on the other extreme, where they are too detailed and may take too much time. As in, to do one simulation, you might be required to spend days to get one result. So the question we asked there was, can we come up with an intermediate method which can give you sufficient enough results to do certain kind of studies, at the same time be accurate enough to make some useful analysis? So what we found was certain questions such as, what is the best combination of a routing strategy on a particular system if you're running a job on a large scale system? Can we try and predict that answer using a modeling technique? Or similarly, what is the best combination if you have parallel workload running on a large system? Or should I be using things such as individual job routing on a large system for doing my particular runs? And this is where we think modeling in a proper manner can help us answer these questions and save time and at the same time make get good results. The network of choice here is Dragonfly. Dragonfly consists of a two-level topology. The first level is a dense connectivity among routers, which forms a group. The connectivity can be an all-to-all, as is being done in IBM Perks, where they take 32 routers and connect them in an all-to-all manner. Or it could be something like what Cray does, where it connects rows and columns in a 2D grid in an all-to-all manner. At level 2, the groups created at level 1 are treated as virtual routers, and all these virtual routers are connected in an all-to-all manner. So in essence, if you want to go from a node in this group to another, you may have to jump to a physical router in your group and then make a global hop, which is the second level hop, and then again do the same thing in the other router. So once we have chosen the topology that we want to analyze, and once we know the questions, we came up with a list of experiments that we want to conduct. And this is what we got. We are looking at a huge set of job placement that whether we want to place our jobs in a random nodes manner, as in you want to randomly sprinkle the nodes that you are allocated in the system, or you want to do a more better blocking system, that you want to allocate groups together to a node and those kinds of things. These combined with various routing strategies which are available on a Dragonfly network, things such as static direct routing or static indirect routing and things of that nature, that combined with common communication patterns such as unstructured meshes, 2D stencils, 4D stencils, all-to-all, and finally parallel workloads. What happens if you combine these individual patterns into a mixture of one or more such single jobs? This is very important because this is what most of the machines actually run when a supercomputer is in production. So if you combine all these things, what we found was there are 360 cases we are looking for, and the prototype system which we were looking at had 92,000 routers, which is 8.8 million cores. So if I wanted to do this using a packet level simulator, last time I checked with Big Sim sequential simulator, one simulation takes 15 days. So 360, yeah, it may finish by the time the next batch graduates, but that's not where I want to go. So what we chose was, okay, let's go for a modeling technique, and we developed a model. The input to this model are the network graph of the Dragonfly we are interested in, the application comm graph that we are interested in, the placement of the applications that we are executing onto the Dragonfly, and the routing strategy. What this model does is, it cannot give you all the information you need. It can't tell you how much time exactly it will take. What it will tell you is a steady state traffic distribution. What it means is, if you ran this pattern in a bulk synchronous manner on the machine, what kind of traffic distribution on various links will you see in a stabilized system? So we are assuming large communication. So as communication happens, the systems react to the communication. There is adaptivity, and eventually there is a stabilization point which the entire system reaches. And if that stabilized state is better than other stabilized state, we assume that this particular placement with routing is better than what we have seen. This model has been implemented as a scalable MPI program which can scale to a few thousand cores. In particular, the runs we did, the maximum time it took with those 8,000 cores was 2 hours. A typical time was around 10 to 15 minutes. Going into the details of model, we begin with 2 copies of the network graph. So essentially, we are given this network graph where we have told what is the bandwidth capacity on various links. So we begin with 2 copies of that graph. One which is called n-alloc, which represents the bandwidth that has been allocated to various communication patterns that are flowing on the network, and n-remain, which is the remaining bandwidth in the system. In the beginning, the n-remain is equal to the capacity, whereas n-alloc is essentially 0. Then in an iterative manner, we try and find this stable state. For example, in the while loop, first we take each message and try and find all the paths this particular message can take between the source and the destination. For example, here, if we are starting with a network which has 10 gigabytes per link capacity and a source and a destination, let's say there are 3 paths, P1, P2, P3. This is a direct path, and let's say this is an indirect path which this has to take. In the next step, all the messages which are going to the network request the links that I want to use you for the communication in the next iteration. So essentially, you collect that request and we get a number. So for example, the path 1 may get request from 1 message, whereas the other path may get message from 2 different messages, and a particular path may get different requests on different links, depending on whether those links are shared among various paths that other messages require. Once we have these links, we calculate how much effective bandwidth can be allocated to a particular message on that path. So since we started with 10 gigabytes, what we find here is that on this path you can give 10 gigabytes to that message. On this path you can only get 5 each, whereas on this path, although this guy could have given 10 gigabytes, since we have to maintain the flow, you can only use 3.33 gigabytes. So in this way, we allocate the new bandwidth to the messages, and using that allocation, we update the n alloc and n remain, and then the cycle continues. We keep on repeating this process till we get a particular stabilized system where no more allocations can happen. Depending on the routing strategy you are using, and depending on your inclination on which message to favor and what kind of adaptivity you want, the allocations in this step and this step would change. So for example, if adaptive routing is being used, we will know that if some link is particularly heavy, we would not request for more bandwidth on that particular link. So at the end, we get the allocations that each messages will get, and using that allocation, we know what distribution of traffic will be there on various links in the system. So based on this model, and using this particular model in the MPI program, we implemented this. We added several capabilities such as multi-job simulation. So one can specify a set of jobs which should be run on this particular location, and their results were observed. So next I'll cover the results, but before that I would like to show how to read a particular plot that I'm going to show. A typical plot is a bar and whisker with a lot of points, but for now I'll say let's focus on 3 of those. The first point to focus is the maximum traffic, which is represented by the horizontal bar at the top. Maximum traffic is important because if there are few links which are heavily loaded, then they cause congestion and they drive the entire network space. Then there is average traffic, which tells you how good your mapping in general is. So if there are 2 mappings where the maximum traffic is similar, but you have more average in one than the other, then maybe you're unnecessarily putting in data on the network, whereas we could have avoided that. And then there is median, which tells you how good the distribution is. Of course, like median by itself would not tell you. The comparison of median with average will tell you whether you are left tail or whether you're right tail, or what kind of distribution are you seeing. So with these results, let's look at the first benchmark. Before that, yeah, what we are looking for is an ideal distribution where the maximum is as low as possible and all the data points. Ideally, I would like it to be such that you can't differentiate between the first quartile, second quartile, and so on and so forth. But typically, you don't get that kind of distribution. So the first benchmark which we studied was an unstructured mesh, where each MPI rank or a core which is being simulated had 6 to 20 neighbors, which they were communicating 512 KB messages. The neighbors here were chosen such that they were they were close in terms of rank. So if I'm a rank 50, my neighbors will be something in MPI rank range 30 to 70. So they're close in MPI rank terms. So what we see there is, we'll focus on the static direct routing first, that as the blocking size of the placement increase, as we go from random random nodes to random routers to random chassis to random groups, so we are giving more and more large blocks of a particular group to the job. The maximum traffic, the average traffic, all those things fall, which is essentially telling us if you have an MPI communication pattern which has MPI locality, you might be better off placing them close by. And as you can see, the maximum would drop by around 90%, whereas the average will drop by around 92%. However, if you use indirect routing, which is somewhere here, what we see is your average will increase because your indirect routing is going to use more and more links in a particular path. However, your maximum will start to decrease. So this maximum in comparison to this maximum is on the lower front. So what it tells us, if you use indirect routing, your average is going up for this pattern, but your maximum is reducing by 50%. So your network is becoming less congested in terms of hotspot, but in general, your network is becoming more congested. And finally, if you had adaptivity, we see somewhat similar patterns as indirect routing, but adaptivity makes sure that your maximum traffic comes down. So in essence, your hotspots are being removed by user adaptive routing. Here, the user adaptive routing led to reduction of 50% in the maximum traffic. But if you change your application pattern, if you go from unstructured mesh to something like a random neighbor or an all-to-all pattern where an MPI rank might be communicating with a large set of other MPI ranks which are uniformly spread in the system, you get a completely different distribution. The impact of job placement is almost negligible. So no matter how you block them, it doesn't matter. Indirect routing has inverse effect. Your average goes up, at the same time your maximum goes up. The reason for this is, if you already have a communication pattern which is well spread in the system, so why do you want to spread it further and add more traffic, so your maximum goes up that way? Adaptivity helps little here because things were already so nicely distributed. Still there's a 10% reduction. Finally, the hybrid routing, which I'm not shown in this graph, which tries to combine the indirect routing and direct routing together, does not perform as well as the indirect routing in this particular case. So we did such similar studies for two more. Yeah. So they have narrow spreads because the way they're implemented, they try and use random links in the system. So they do not try and follow a particular set path. So even if I'm talking to someone who's close to me physically, they do not account for that. They always try and go somewhere in the system and come back to me. Average load. Yes. Because you're more uniformly distributing. Yes, that's right. So we did similar studies for 2 or 3 more single benchmarks. The results are in the paper. I would not cover them right now. But what we also did was, we tried to create parallel workloads. So we took these single patterns and we placed them on the system with different core counts. For example, in workload 1, what we said that 20% of the system was being occupied by an unstructured mesh pattern, whereas 20% is occupied by many-to-many and so on and so forth. And we did this kind of changes for workload 2, workload 3, and workload 4, and then we ran the model again and tried to see where the results go. The striking feature is, no matter how we tried to divide them, as long as the jobs were large, so like 10% or 20%, the patterns look very similar. You have workload 2 here and we have workload 4 here. Both of them have very similar looking distribution in the system. Again, I've dropped the static direct routing and static indirect, because what we observed was adaptivity was always helping. It was never being negative. So we dropped those results. The other interesting thing which came up with workloads was that the hybrid routing, which was so far not being best in any case, it starts to be the best. It tries to combine the good features of indirect routing and direct routing and learn from that and give you the best performance if you have a workload. Typically what happened was, if we also did analysis of per job traffic and those kinds of things, and what we found was that if your pattern was such that it was being benefited from indirect routing, that hybrid routing will start shifting more towards that. And if you have a collection of that, those kinds of effects become more prominent. And finally, we did the comparison of job-specific routing, in which what we said was, you have these 5 jobs in the workload. What if we let them use the routing which is best for them? So when we ran them individually, different routing performed best. So in this case, we said, okay, you can use the routing which is best for them. And what we observed was the pattern was very similar to what hybrid routing showed us, but the maximum traffic went down again. So that was in some sense interesting, that if you let jobs decide by themselves, they would not have detrimental effect on the entire system. One can say that this is for a very small set of workload, I agree, but that's where the pattern, that's what the pattern is, what we saw. So just to summarize, in this work, what we learned was that fast analytical methods have their use case. They can help us do these kinds of study which are currently not possible with more detailed approach. Adaptivity is good. Everybody should try and adopt it. There have been cases where people have contended that adaptivity may lead to too much overhead, but if you have communication intensive applications, that overhead is easily subsided by what the gains we see. What is the best combination for single jobs? As I showed, it depends. What kind of job are you looking at? If you have a job which has MPI rank-based locality, you benefit by blocking, but if you have a job which is already well spread, don't use indirect routing, use direct routing, and don't try and spread them. For workloads, as I said, hybrid routing does help, so that's where we should try and go towards. And randomized placement at node or router level is good. Any more blocking for hybrid routing, for hybrid patterns, was not good. And finally, what we also saw was that job-specific routing may have its benefit. You should allow, the systems should allow jobs to choose the routing strategy if they know what they are doing, and that may get us some more performance. I leave you guys with a set of relevant publications if people are interested in studying more about these topics. I can take questions at this point. So I don't remember the number directly, but every time we have tried to use mapping for things like OpenAtom, which is very communication intensive, or NAMD even, which does not have that much communication, but the impact can be up to 30 to 40%. So typically what happens is, even at low scales, if your application doesn't show this kind of behavior where communication is impacting, as the system size increases due to the interference from other jobs and due to increase in diameter, particularly on torus, your communication time dominates, and that's where these kind of things help a lot. So the answer is it depends in some sense. For example, if you're on torus network, and if you're running an application which is not bisection bandwidth bound, it's only bound by nearest neighbor communication, then you don't want to exploit that. You still want your application to be in a nice cuboid. But if your application is bisection bound, you want to use the entire bisection, and then if there are cores left in the middle, you can sprinkle the non-communication oriented application in middle of that. On larger systems like Dragonfly, I think it's very important because you have indirect routing, you want a nice spread, you want to reduce the amount of indirect routing you do, and that's where I think it's most beneficial.